In this video, I will demonstrate how to calculate or to create a receiver operating characteristic curve. Now, these are useful ways to interpret the sensitivity and specificity levels of diagnostic tests. In other words, situations in which we're using a test score, typically a quantitative score, in order to try and predict some kind of a dichotomous outcome. So in the example that we're going to do in this video, we have a balance test score, a numeric balance test score that we've created and we've administered to a group of subjects. And then we're going to see if that balance test score can predict whether or not they have a history of falling and having fall-related injuries. So we're going to see if this quantitative test measure can then be able to help us predict the accuracy in predicting whether or not someone's going to fall into some sort of a dichotomous outcome. Now, this could be developing an injury or an illness, or this could be having the presence of an injury or illness, so it can be used quite often in order to determine how well a diagnostic test is actually predicting the outcome. Now, a little bit of history as far as receiver operating curves or characteristics. This came from part of a field called signal detection theory, and this was developed during World War II for the analysis of radar images. So radar operators had to be able to decide whether a blip on the radar screen represented an enemy target, a friendly ship, or maybe just random noise. So signal detection theory measured the ability of radar receiver operators to make these important distinctions. So their ability to do so was called the receiver operating characteristic. And it wasn't until much later in the 1970s and 80s that signal detection theory was recognized as being really useful for interpreting diagnostic test results. So that's where this theory and this idea comes from. And so we're going to be able to use statistical analysis to develop some understanding of how accurate a test might be. So some characteristics of these curves are they're really a generalization of the set of potential combinations of sensitivity and specificity possible for a predictor. So as we know, sensitivity and specificity are not mutually inclusive. We can have a high value of one and a low value of another. So the ROC curve helps us kind of determine this trade-off between these two measures, sensitivity and specificity. So these curves can help us kind of provide a natural scale for comparing different predictors that are measured in different units. Now, an overall indication of the diagnostic accuracy of a ROC curve is termed the area under the curve, or the AUC. Now, AUC values closer to 1 indicate the screening measure reliably distinguishes among subjects that have the outcome of interest or don't have the outcome of interest. In this case, a history of falling or not having a history of falling. So the data we're going to look at then is in two columns. So the column on the left is the score on this balance test, and the lower the score, the less balance ability or the more poor balance ability the subject has. And the next column is the outcome that we're trying to predict, and this is whether or not the subject has a history of falling. So having a score of 0 in the outcome means they do not have a history of falling, and having a score of 1 on the outcome means that they do have a history of falling. So what we want to try and do is see if the score on this balance test can predict whether or not someone's going to have a history of falling. And so that way we could then use it to design some kind of an intervention to maybe prevent falling. So in order to compute the ROC curve, we want to go to the Analyze menu and then go down towards the bottom of the menu where you see ROC curve and click on that. Now in this box we want to move our variables into their proper place. So the screening measure that we're using is the test variable. So in this case it's balance assessment. So that gets moved into the test variable box. And then our dichotomous outcome variable gets moved into the state variable box, in this case, history of falling. Now, what we need to do next is designate to SPSS what numeric value we are giving for subjects who have the outcome of interest. In other words, subjects who have a history of falling. So we're using a value of 1 to indicate a positive outcome. In other words, they have the outcome that we're interested in. Okay, so in the box that's labeled display, we want to click on ROC curve, and then we also click on with diagonal reference line, and this gives us kind of a null hypothesis. In other words, if the test has no accuracy or no sensitivity or specificity whatsoever, our ROC curve would actually look like a diagonal line. So what we're looking for is a curve that resembles, to a certain extent, a bell curve. And so we can use that to kind of get a reference idea of how much sensitivity and specificity our test actually has. The next thing we want to do is click on standard error and confidence intervals. So this is going to give us a standard error of our measure, as well as 95% confidence intervals for our area under the curve, which is what we're going to use to evaluate the accuracy of the test. Okay, the next thing we do is click on the options button. And under classification, we're going to leave checked include cutoff value for positive classification. So this will give us an idea of what score we can use as a cutoff value to indicate a positive outcome or a negative outcome. In other words, has the condition or doesn't have the condition. So we're going to leave that check there. The next is labeled test direction. Now we need to tell SPSS which score on our screening tool we are assuming will be related to a more positive test. So what we're saying here is a small score on our balance test is associated with more poor balance, which should then predict a history of falling. So we want to check a smaller test result indicates a more positive test. In other words, they're more likely to have the outcome. All right, and the rest stays the same, and we just click continue, then we click OK. Now the first thing we can look at in our output is the case processing summary, and this gives us an idea of how many of our subjects tested positive for the outcome, in other words, had a history of falling, and how many tested negative for the outcome. So of our subjects, we had 32 subjects that were actually positive for a history of falling, and 93 of them were negative for a history of falling. Now the next thing we can look at is the actual ROC curve. So again, this green line represents the null hypothesis. This is a curve that has absolutely no value, or represents a test that has absolutely no value, 0 sensitivity, 0 specificity. So that would be a worthless test. Now the curve that we're looking at is related to our data is this blue line. And as you can see, it's somewhat jagged. It's nice when it's nice and smooth, but very rarely does that turn out to be the case. So as we look at this line here, this represents the curve of the scores relative to the outcome. So this represents the sensitivity and specificity of our test. And so what we want to try and quantify is the area under this curve, and that will give us some understanding of how accurate the test is. And so an area of 1, an area under the curve of 1 represents a perfect test. In other words, it has perfect sensitivity and perfect specificity. An area under the curve of 0.5 or less represents pretty much a worthless test. So a rough guide for classifying the accuracy of a diagnostic test using area under the curve is that if the area under the curve is between 0.90 and 1, that would be an excellent test. In other words, it has a very, very high level of sensitivity and specificity. If the area under the curve is between 0.8 and 0.9, that would be a good test. In other words, it has pretty good usefulness. A score between 0.7 and 0.8 would be a fair test. It has some uses, but it's not, shouldn't be considered to be terribly reliable or accurate. A score between 0.6 and 0.7 would be poor. In other words, I would rarely use that test because of its combination of specificity and accuracy. And then anything that's at 0.6 or below I would consider to be a worthless test. It's not worth using because it does not predict outcomes very well. So it looks like we have a curve that mimics to a certain extent the bell curve, which is a good sign. That means we're going to have a fairly large area under the curve. So the next table we want to look at that gives us our final interpretation is the area under the curve table. So the first thing we can look at is the box labeled area, and this gives us our actual area under the curve. And so our test has an area under the curve of 0.849, which falls almost smack in the middle of that good range. So I would say this is a fairly useful test. In other words, it has a good balance of sensitivity and specificity. We can also look at the standard error, and that's the standard error of the area under the curve. We can also look at the significance value, and again we can use this to develop some statistical significance for our ROC curve, and this is values less than 0.05. So we would say that this is a statistically significant ROC curve, in other words, giving evidence of the accuracy of our test. And then lastly, we can look at the 95% confidence interval of the area under the curve. So this is telling us that if we were to do this with 100 samples of subjects, 95% of the samples would have an area under the curve that ranges between 0.758 and 0.94, which keeps us in that fair to excellent range. So that would indicate that, again, we have a test that is likely going to be minimally somewhat useful, and at maximum is going to be very useful and very worthwhile. So to summarize, I demonstrated how to perform receiver operating characteristic analysis to help us determine the accuracy of a diagnostic test, and this gives us an idea of the sensitivity and specificity of the test and allows us to interpret a little bit more in detail how accurate the test is overall. So hopefully you learned something from this video, and good luck in using this technique in your own research.